13.8 billion years ago. What we know as our universe began with the hot Big Bang. The universe was extremely hot and dense, yet it was also expanding and cooling. It was made up of matter, antimatter, and radiation. The volume of our observable universe has grown to 46 billion light-years in radius by now, and the limit of what we can measure corresponds to the light that is currently reaching our eyes. Even while that distance is huge, it's not infinitely large. It's merely the limits of what we can observe. What lies beyond that? What about the unobservable universe? Is it possible to determine whether the universe we live in is limited or infinite? That is, whether there is an end to what we refer to as the universe, or whether it is infinite beyond our measurements and knowledge. In this documentary, we embark on a journey beyond the known, delving into realms of theoretical physics, mind-bending concepts, and the mysteries of what might exist beyond our cosmic doorstep. To answer the question of what's outside the universe, we first need to understand exactly what we mean by universe. Have you ever wondered how vast the universe is when gazing up at the night sky? What if I told you that it is so big that we are unable to see it all? The observable universe is the region that is visible to us. We are positioned exactly in the center of what appears to be a massive cosmic bubble. Let's dive into the fascinating world of the observable universe and see just how big it is. If you were to step outside right now, you'd only be able to see so far horizontally. Your vision would eventually reach the horizon, beyond which you would be unable to see much. You're aware, however, that life exists beyond the horizon. There is more on this planet than what you can see. Furthermore, as you look 360 degrees around you, it appears as though you are at the center of the world, even though you know that isn't actually the case. That is how it appears from any point on Earth. In the same manner, our view of the universe is limited to what is visible to us on Earth, and it is probably infinite in size. We can see only as far as our cosmic light horizon. Because we are unable to see the entire universe, it may appear to us that we are the center of the universe, but this is only an illusion. Light, which travels at a fast but finite speed, has simply not reached us from more distant parts of the entire universe. The entire universe and the observable universe are therefore very different from one another. All that we have seen or been able to see up to this point is the observable universe. On the other hand, everything that exists, has existed, or will exist is referred to as the entire universe. More specifically, the observable universe is the region of space visible to us from Earth. The term observable in this context does not mean that there is anything to be detected, nor does it apply to the ability of modern technology to detect light or other information from an object. It refers to the physical boundary defined by the speed of light. There is no signal that can move faster than light. Because the signals could not have reached us yet, there is a maximum distance, known as the particle horizon, beyond which nothing can be observed. Astrophysicists sometimes make a distinction between the visible and observable universes. The former includes signals since the end of the inflationary epoch, while the latter includes only signals emitted since recombination. But how distances in space are measured? Astronomers use different techniques to measure cosmic distances. Basic trigonometry, similar to what you studied in high school math class, can be used for measuring things that are quite close, such those in our solar system and even in our small neighborhood of the Milky Way within 100 light years. With the help of the parallax method, the distance of faraway objects can be measured or estimated. When you look at your finger through your left eye while closing the right eye, and then look at your finger through your right eye while closing the left eye, you would notice that the position of your finger seems to change with respect to the point on the wall. This is called parallax. By measuring this small change and knowing the distance between your eyes, you can calculate the distance to your finger. That's trigonometry. When it comes to measuring distances to other stars, there are no two eyes that could do the trick. Instead, the orbit of Earth around the Sun provides the baseline for these calculations. Simply, if you take a star's position once a year at one point in the sky, and then again 6 months later, you will have a relative position of the nearby object in relation to the far more distant stars in the sky. Thanks to the Pythagorean theorem, you can determine the distance if you know the size of Earth's orbit and the angle of light in those two measurements. Nevertheless, a star's shift decreases with distance, making it difficult to measure this angle and requiring the use of some more advanced method for measurement. Once trigonometry is no longer a useful technique, astronomers look for Cepheid stars, which are extremely bright and common stars. These specific stars were first identified in 1794 and have an ability to pulse, becoming dimmer and brighter in predictable cycles. Surprisingly, the longer a Cepheid takes to pulse, the brighter the star is in reality. Similarly, the shorter the pulsation duration, the dimmer the Cepheid. What's more, these pulsations are directly related to their absolute luminosity, which occurs within well-defined and predictable time periods, ranging from 1 to 100 days. Just like if you saw a candle right in front of you and another very far away, the one closer to you would appear much brighter. And hence, the true brightness of those stars can be determined, and consequently, their distance by measuring nearby Cepheids and comparing the length of their pulsation period to those of those Cepheids that are farther away. Cepheid variables can be seen and measured to a distance of about 20 million light-years, compared to a maximum distance of about 65 light-years for Earth-based parallax measurements and just over 26 light-years for the ESA's Hipparcos mission. They can serve as standard distance markers, constituting yet another crucial step on the cosmic distance ladder. Even though 20 million light-years sounds like an enormous distance, the cosmos is 1,000 times bigger. Thus, we need to add another step to the ladder. This is when supernova, especially those from specific binary star systems, come in rather handy. One star in these two star systems dies and turns into a white dwarf, while the other star continues to exist. After that, the white dwarf starts to consume the surviving star and gets bigger until it has roughly 1.4 times the mass of the Sun. At that moment, there is a massive explosion that releases more energy than entire galaxies and is visible over half of the observable universe. We refer to this as a Type 1a supernova. Astronomers can determine the absolute brightness of the explosion and consequently the approximate cosmic distance to those distant galaxies, because we know how much mass is exploding. At even greater distances, into the tens of billions of light-years, the Hubble constant comes into play. Named after Edwin Hubble, this is the unit of measurement for the expansion of the universe. This is where the whole debate starts to get a little complicated. The universe has been getting bigger since the Big Bang kick-started the growth some 13.82 billion years ago. In reality, the acceleration of the cosmos is increasing with its size. What's interesting about the expansion is not only the rate, but also the implications. If the universe's expansion starts to slow down, it suggests that there is something there causing the growth to slow down. This might be dark matter, which is invisible to conventional instruments. However, if the growth increases, it is possible that dark energy is driving the expansion at a quicker rate. Astronomer Harlow Shapley's observation in 1929 suggested that galaxies appear to be moving away from the Milky Way. Hubble found that the farther these galaxies are from Earth, the faster they appear to be moving. Although the phenomena was formerly thought to be galaxies moving apart, astronomers now understand that what is really being seen is the universe expanding. You would observe the same occurrence happening at the same speed everywhere in the universe. As better and more sensitive telescopes have been used to conduct the measurements, Hubble's original calculations have been refined over the years. According to observations made recently by several telescopes, the universe is expanding at different rates depending on where you look. The Planck telescope measures the expansion of the more distant background universe, which is expanding at a slightly slower rate of 41.6 miles per second or 67 kilometers per second per megaparsec, compared to the Hubble Space Telescope and Gaia Space Telescopes, which measure the expansion of the nearby universe at 45.6 miles per second, 73.5 kilometers per second per megaparsec. It may be hard to imagine, but the universe is not only expanding at an ever-increasing rate in all directions at the same time, but the space between objects in the universe is also expanding. Everything is moving away from everything else, and it is moving faster and faster all the time. This inter-object expansion and acceleration is related to dark energy, which is beyond the topic of this discussion. Therefore, the further away you look, the faster the galaxies are moving away from us. Galaxies that are very far away can be measured for distance by measuring their redshift, which tells us how quickly they are moving away from us. Astronomers use redshifts to measure the expansion of the universe and consequently the distance to the oldest and most distant objects in our universe. But what is a redshift? It is often compared to the high-pitched sound of an approaching ambulance siren that becomes lower as it passes by and eventually goes away from you. The reason behind the change in an ambulance's sound is the phenomenon known as the Doppler effect. It's an excellent comparison because waves, which are affected by their motion through space and air, carry both sound and light. Sound travels through the air at a maximum speed of 750 miles per hour or 1,200 kilometers per hour. The sound waves in front of an ambulance get compressed as it rushes forward and blares its siren. The sound waves behind the ambulance, meanwhile, begin to spread. This means the frequency of the sound waves is higher ahead of the ambulance, means more sound waves will strike a listener's ear over a set amount of time, and lower behind it means fewer sound waves will strike a listener's ear over a set amount of time. Pitch shifts are interpreted by our brains as variations in the frequency of sound waves. Similar to sound, light is a wave that moves at a fixed speed of 186,000 miles per second or 300,000 kilometers per second, or around 1 billion kilometers per hour. Thus, light follows the same rules as sound. Galaxies are, as we know, moving away from us. Similar to how an inflated balloon would cause a wave created on its fabric to be stretched, the wavelength of light is stretched when galaxies move away from us. Through the use of a prism or a comparable telescope-suitable instrument, like diffraction gratings, we can see an array of absorption lines from elements like sodium, hydrogen, and so on. All those absorption lines, however, experience a Doppler shift and go toward the red portion of the spectrum if that galaxy is speeding away from us. We refer to this as a redshift. The opposite occurs for galaxies that are moving toward us. They are blue-shifted. Astronomers usually only use the phrase redshift to make things simpler. If a blue shift is occurring, they simply place a negative sign in front of it. A galaxy's redshift increases with galaxy distance from Earth. As a result, the redshift of a galaxy at the cosmic light horizon, the outer end of our observable universe, is nearly infinite. This indicates that the light coming from that distant galaxy has very little energy, which is why we can hardly see those galaxies with the visible light spectrum. When Hubble looked at the light from distant galaxies through a prism, he observed a redshift away from known variable for the color. Hubble discovered that nearly all of the galaxies he examined had this redshift, which indicates that they were traveling away from us. Extremely far galaxies' distances could be determined with a fair degree of accuracy by plotting various redshifts and known distances on a graph. This is the last measuring tool and serves basically as the universe's baseline for distances. The remaining radiation from the Big Bang, or the moment the universe first began, is known as the cosmic microwave background. According to theory, the cosmos experienced rapid cooling, expansion, and inflation during its birth. The heat left over after the Big Bang is represented by the cosmic microwave background. The cosmic microwave background is present across the cosmos, yet is invisible to the unaided eye, because it is so cold, just 2.725 degrees above absolute zero, or minus 273.15 degrees Celsius, it is invisible to humans. This indicates that the electromagnetic spectrum's microwave region is where its radiation is most noticeable. The cosmic microwave background goes back to some 400,000 years after the Big Bang, and as we all know, the universe started 13.8 billion years ago. This is due to the fact that the universe's temperature was extremely high in its early phases, when it was just 100 millionth of what it is today. Any atoms that were there at the moment broke rapidly into protons and electrons, which are tiny particles. The electrons scattered the CMB radiation in the form of photons, which are particles that represent light quantum states or other types of radiation. In the same way as optical light wanders through thick fog, photons also traveled around the early universe. The universe was cool enough for hydrogen to form some 380,000 years after the Big Bang. The CMB photons move in straight lines because collisions with hydrogen hardly affect them. The point at which CMB photons last collided with matter is known as the surface of last scattering. Beyond that point, the universe was too big. This means that when we map the cosmic microwave background, we are gazing back in time to 380,000 years following the Big Bang, right after the radiation-opaque universe. In 1948, American cosmologist Ralph Afer made the first prediction about the CMB, while collaborating with Robert Herman and George Gamow. The group's study focused on Big Bang nucleosynthesis, or the synthesis of elements other than the lightest hydrogen isotope type in the universe. This kind of hydrogen was produced very early in the history of the universe. But the discovery of the CMB was accidental. Arno Penzias and Robert Wilson, two Bell Telephone Laboratories researchers, were developing a radio receiver in 1965 and were perplexed by the noise it was taking up. They quickly discovered that the noise originated from every direction in the sky. In the empty space between stars, this radiation is the oldest and furthest radiation yet found. This essentially means that the furthest back in time we can see is 13.8 billion years, because it has taken 13.8 billion years for light, while moving at the speed of light, to reach us. Therefore, the observable universe has a radius of 13.8 billion light-years. Furthermore, no matter which way we look, the light we see has only been traveling for a maximum of 13.8 billion years, because the universe is only around 13.8 billion years old, and light takes time to travel through space. Given this, one would naturally assume that the observable universe would be 2 times 13.8 light-years across. However, this is not correct. That's because space has been expanding over time, pushing the far-off objects that released that light 13.8 billion years ago even further away from us. Recall the Hubble constant and how it was used to measure the universe's expansion. The universe has been expanding over the 13.8 billion years that the light from the CMB has been moving toward our eyes, pushing the edge of the known universe farther out, even though humans aren't technically able to see that far. The current location of the photon's origin, as determined by the Hubble constant, is an astounding 46 billion light-years away. Thus, the observable universe's diameter, calculated by multiplying by 2, is thus 93 billion light-years. Clearly, calculating distances of this magnitude can bend the brain beyond the realm of human comprehension. Fortunately, with the cosmic distance ladder in place and plenty of astronomers well versed in these types of measurements, we're able to keep tabs on how the universe is moving, as well as our place within it. Upon totaling all the galaxies in this region of space, we would discover that our observable universe contains an astounding 2 trillion of them. You may think that there would be no upper limit to the amount of the universe that could be seen if we waited an arbitrarily long amount of time and that we could see an arbitrarily vast distance. But in a universe with dark energy, that simply isn't the case. Dark energy is expanding the fabric of space at such a rate that GNZ11, the high redshift galaxy, is moving away from us at an estimated speed of 426,182 miles per second, or 687,000 kilometers per second, over twice the speed of light. Further off objects will appear to gradually disappear from our perspective as time passes in a universe powered by dark energy. There's always more to discover in the universe, but the amount that can ever be observed by humans is finite. We can determine what we refer to as the future visibility limit, or the farthest distance humans will ever be able to observe, based on the rate of expansion, the amount of dark energy we have, and the current cosmological parameters of the universe. Our current vision limit is 46 billion light-years in a universe that is 13.8 billion years old. Our maximum visibility in the future will be around 33% larger at 61 billion light-years. There are currently galaxies out there whose light is headed toward our eyes, but hasn't had a chance to reach us yet. There are more galaxies yet to be discovered than there are in the visible universe, which might surprise us if we were to add up all the galaxies in the regions of the universe that we will one day see but are not able to access now. In addition to the 2 trillion galaxies that are currently visible to us, there are an additional 2.7 trillion galaxies just waiting for us to see. Our measurements of these occurrences would indicate if the universe had a finite size, an edge, or if its properties started to change as we peered to higher distances. The unobservable universe is at least 250 times as large as the presently visible part. We'll never be able to observe anything approaching those great distances. We will be able to see objects up to 61 billion light-years away from us in the future, but no further. It will reveal slightly over twice the amount of the universe that is currently visible to us. In contrast, the unobservable universe has to have a diameter of at least 23 trillion light-years and include a volume of space that is more than 15 million times larger than what is visible to people here on Earth. But when we consider the universe beyond our current limit for observation, it's important to keep in mind just how little of that universe we can truly reach or explore. Everything we can't wait to see depends on light that was already released billions of years ago, precisely at the time of the Big Bang. As things stand right now, humans could not possibly reach almost all of the galaxies in space, even if we fled at the speed of light. Not only is the universe expanding, but distant galaxies appear to be moving from us faster due to dark energy. The limit of what we can observe today is far smaller than the 4.7 trillion galaxies that we will eventually be able to observe out to a distance of 61 billion light-years. To put it another way, there will be 4.7 trillion galaxies for us to view in the future. Not many of them will ever see us as we are now, and most of them will only ever see us as they were in the very distant past. Of all those galaxies we'll someday see, 4.634 trillion of the galaxies are currently unreachable, even traveling at the speed of light. Someday far in the future, it will arrive at our eyes. As time passes, and the light from the final galactic holdouts continues on its inevitable journey towards us in the expanding universe, we get closer and closer to our ultimate cosmic viewpoint. All of that contributes to our understanding of the night sky's darkness. The expanding universe theory also contributes to the understanding of why our night sky is dark and how it relates to the observable universe. Now, what about the center of the universe? We are the center of the observable universe after all. Since the observable universe is limited to the space that is visible from Earth, we are in the center of it. And kind of like how the view from a very tall tower is a circle centered on the tower, the piece of space we can see from here is naturally centered here. To be more exact, each of us is the center of our own observable universe. But that does not imply that we are the center of the universe as a whole, just as the tower is not the center of the Earth. Up to the horizon, it is the center of the portion of the world that it can view. That doesn't mean there isn't anything there, though, simply because you can't see past the horizon. Similarly, the observable cosmos is no different. Gazing up at the sky, we observe light coming from matter that is currently 46 billion light-years away and with a maximum age of 13.8 billion years. But beyond that, there ought to be much more universe beyond the limits of what we can presently see, the unobservable universe. Our field of view into the universe is expanding exponentially. All we need to do is watch and wait for the universe to age and light from farther away to reach us. Despite all of the techniques of measurement, the universe's true size remains uncertain. It might be infinite, and portions of it remain outside the observable universe because they are too far away for Earth or our equipment to have received any of the light emitted since the Big Bang. Although detailed maps of the universe's oldest light have been made possible by the European Space Agency's Planck space project, the size of the cosmos is still far beyond our understanding. According to inflation theory, the universe may be infinite, and the visible universe is only a small portion of it. The size of the universe is also determined by its shape, which can be anything from a closed sphere to an endless, flat surface. The theory of general relativity, under which space itself can curve, allows for the universe to take one of three forms: flat, like a sheet of paper, closed like a sphere, or open like a saddle. The fate of the universe depends on this cosmic geometry. The universe's shape provides information about both its past and future. For example, it can reveal whether the universe is infinite or finite, and whether it will continue to expand indefinitely or finally collapse. For a matter that bears on such grand questions, its components are remarkably simple. The density and the rate of expansion of the universe are the only two parameters that determine its final structure. Dark energy makes up about 68% of the universe, whereas dark matter makes up 27%. Planets, stars, and other bodies are comprised of normal matter, which makes up the remaining portion. The amount of matter contained in a specific volume of space is referred to as the universe's density. The universe can curl into a ball if its density is high enough to overcome the force of expansion through gravity. This is referred to as the closed model because of its sphere-like positive curvature. A mind-boggling property of this universe is that it is finite, yet it has no bounds. However, space will warp in the opposite direction if the universe has a low density and is unable to stop expanding. This would create an open universe with a saddle-like negative curvature. The most likely possibility for the universe, according to scientists, is the Goldilocks scenario. The majority of cosmological data suggests that the universe extends in all directions without curving positively or negatively, and that its density is around 6 protons per 1.3 cubic yards. To put it another way, the universe is flat. Perhaps this will come as some consolation to anyone disappointed by our planet's roundness. Current observations and measurements of the curvature of the universe also indicate that it is almost perfectly flat. This may lead one to believe that the cosmos is infinite. However, it's not that easy. It is not necessary for the universe to be infinitely big, even in the scenario where it is flat. Consider the surface of a cylinder, for example. It is geometrically flat because parallel lines drawn on the surface remain parallel. That's one of the definitions of flatness. And yet, it has a finite size. The same could be true of the universe. It could be completely flat, yet closed in on itself. Still, what does a flat universe mean? Although this flatness isn't the typical two-dimensional kind we see in daily life, there are a few examples that can help you picture it. Imagine yourself in a square room, standing at one corner. Turn 90 degrees after moving 10 feet along the wall to the next corner. Take 10 more steps and make another 90-degree rotation. Once you finish 2 more of these, you will find yourself back at the beginning of the square. We all studied ordinary Euclidean geometry in high school, and adding one additional dimension results in a flat universe. However, the results would be different if this experiment were carried out on a positively curved space, which is a representation of a closed universe. In the closed world example, Returning to the starting point required only 3 turns, however. In the flat universe example, it required 4. In case you're still not clear, here's another illustration. 2 rockets traveling close to one another in a flat universe will always remain parallel. This is unlike a closed universe in which the paths of these 2 rockets will diverge, trek along the curvature of space, and eventually loop around to meet where they started. In an open universe with a negative curvature, the rockets will separate and never cross paths again. The cosmic microwave background, or the afterglow of the Big Bang that radiates toward us from all directions, contains the best hints about the structure of the universe. Scientists have been measuring temperature variations in the CMB for several decades, effectively doing trigonometry at the greatest scale imaginable, and have found nearly no curvature at all. A flat universe is a key piece of the standard cosmological model, also known as the lambda cold dark matter (LCDM) model. Lambda is the Greek letter for lambda, denoting dark energy. Additional evidence for flatness comes from baryon acoustic oscillations, which are the traces of primordial sound waves left on galaxies after the Big Bang. As we continue to explore and map the cosmos, the universe's immensity serves as a humbling reminder of our place within it. The actual size of the universe may remain one of science's greatest mysteries, even though we may get closer to making more precise measurements. Let's make a comparison between the observable universe's size and some more recognizable things. The observable universe is so big that it could fit around 1 septillion Earths, a 1 followed by 24 zeros inside of it. That is equivalent to more Earths than there are sand grains on all of the world's beaches. One would assume that the observable universe must be densely packed with matter given its vast size. Well, and it isn't. The observable universe is thought to contain several hundred billion galaxies. There are billions or possibly trillions of stars in each of these galaxies. In reality, however, the majority of the observable universe is empty space. The likelihood is that if you choose a random location in the observable universe, you will end up in empty space rather than close to a star or galaxy. We are actually looking back in time when we gaze far into the observable universe because light takes time to travel. The length of time it takes for light from a star or galaxy to reach us increases with its distance from us. Therefore, the observable universe is not only a location, but also a cosmic history book. Just because we can't see things beyond our fiery horizon, it doesn't mean that there's nothing there. As if the mysteries of dark matter and dark energy weren't vexing enough, another baffling cosmic puzzle has been discovered. Whole galaxy clusters have been observed to be traveling in sync toward a single sky point by astronomers. The researchers even speculate that a force beyond the observable world may be to blame for this unexpected motion, which doesn't seem to be related to the universe's expansion. The finding has been named dark flow. According to astronomers, there may be dark flow or unobservable external forces originating from vast structures outside of our universe that we are now unable to fully understand. Studying massive clusters of galaxies, among the biggest structures in the universe, scientists found the flow. These clusters are made up of thousands of galaxies grouped together with extremely hot gas that produces X-rays. Scientists investigated the motion of clusters by analyzing how X-rays interact with the cosmic microwave background, which is leftover radiation from the Big Bang. The CMB's temperature is changed by the X-rays scattering photons, a phenomenon called Sunyaev-Zeldovich effect. A team of scientists, led by astrophysicist Alexander Kashlinsky of NASA's Goddard Space Flight Center in Greenbelt, Maryland, discovered this effect after studying a massive catalogue of 700 clusters that were as far apart as 6 billion light-years, or half of the universe. This effect had not previously been observed as a result of galaxy clusters. They compared this list with the Wilkinson Microwave Anisotropy Probe satellite map of the CMB from NASA. They found that the clusters were traveling in the direction of an area in the sky, between the constellations of Vela and Centaurus at around 2 million miles per hour, or 3.2 million kilometers per hour. This velocity is not the same as the universe's outer expansion, which is accelerated by a force known as dark energy. Scientists discovered a very significant velocity, and this velocity does not decrease with distance. The flow that astronomers detect simply cannot be produced by matter in the observable universe. Scientists concluded that whatever is causing the clusters to move around must exist outside of our observable universe. While inflation theory predicts many strange aspects of the far-off universe, few scientists were able to predict the dark flow. Dark flow structures might be a component of an unknown higher dimensional creation. Surely, you're wondering whether things can get any stranger at this point? Well, the next potential theory is based on the physics of the very, very early universe right back during the Big Bang. Our universe resembles a bubble. Beyond it, other bubble universes can be found, all submerged in the multiverse, an endlessly energizing sea. The concept of a multiverse, which consists of worlds similar to our own, but with some subtle differences, originates from two places in theoretical physics. One comes from our understanding of many branching possibilities in subatomic experiments through the lens of quantum mechanics. The other is a little more concrete, coming from our theories of the extremely early universe. However, we must begin with the universe in order to reach the multiverse. The universe is all the things by definition. It is the whole of all physical reality. If it's a thing, it's in the universe. However, we can begin to open the door to other worlds even with that definition, realizing that light can only move at a finite pace, and that the universe is only a certain age is one approach to do that. As we've already covered, our ability to witness the universe is limited, but that explanation gives you a very weak understanding of the multiverse. Actually, there's more to the universe than what we can observe, so there's more stuff out there. More stars, more galaxies, maybe even more intelligent creatures than we could ever make contact with. All of these things are in the universe, but are definitely not a part of our own world. Those regions outside our observable bubble of the universe still look and act the same as inside it. It's all the same physics at play, just with various other combinations. But that's not where the story has to end. As of right now, our knowledge of the Big Bang's earliest moments is limited. We are aware of the basic picture. Our universe used to be much smaller and hotter. Today, it is considerably colder. We've also put this fundamental theory to the test using a range of studies. However, when we go all the way back to the Big Bang, we get to a point when our understanding of physics fails. The conditions in the universe, when it was younger than a second old, were so extreme that there isn't a single physics theory that can help us. Nevertheless, We believe that the cosmos experienced inflation, an extreme transformation in its early stages. It appears from all available evidence that when our cosmos was only a fraction of a second old, it rapidly expanded to enormous proportions, growing by at least a factor of 10 to the 60. The rest of the Big Bang, when our universe was saturated with particles and radiation and gave rise to stars, planets, and galaxies, was set in motion by this inflationary event. This is where the multiverse comes into play. Perhaps inflation never stopped. Perhaps the universe is expanding at an uncontrollably fast rate all the time, but some of it splits off and becomes calmer. Thus, what we call the universe is just a tiny bubble of the true, ever-inflating, ever-expanding, huge universe. According to this theory of inflation, the universe is always expanding. It just never stops expanding at a rate that is faster than the speed of light. A region simply slows down and pinches off due to a random quantum fluctuation. The rest of the world outside of our bubble keeps doing what it normally does and just so happens to have stopped randomly, while our patch, or bubble of the universe, has simply happened to stop expanding compared to the larger universe. Our patch is not alone. Different patches can also randomly settle down and become a normal, calmly expanding universe. To observers in any of those patches, the universe will appear to them as having a big bang in the past, a universe full of matter and radiation, and an observation limit just like it does to us. These patches, or bubbles, appear to be individual universes in this scenario of endless inflation, divided from one another by a continuously growing expanse of absolutely nothing. This multiverse, a collection of independent, distinct universes full of creatures, stars, planets, people, each doing their own thing, is physically driven and potentially very real. In the multiverse, our universe is not the first bubble to arise, but merely one of an infinite chain of universes. Picture a massive foam, like to the surface of a bubble bath. The multiverse is the foam itself, always expanding and forming new bubbles, each of which functions as a separate universe unto itself. Each of these bubble universes exists inside the same space-time structure. If you point your finger in any random way, there is another world out there, past some unfathomably great distance, and beyond that, another, and still another. There are an endless number of worlds in the multiverse if this type of inflation really never ends. While it is possible that all of those universes ended their local inflation in the same way, it is also plausible that as each universe pinched off, it got a brand new set of physics to go along with it, with different collections of forces and particles. Some of those universes would look incredibly similar to our own. Others may have failed, full of nothing but void. Some may be far stranger than we can possibly imagine, and some might be our exact clones. If, and this is a big if, there are only a finite number of ways to arrange all the particles in a given universe, then with an infinite number of universes, you're bound to get repeated copies. This implies that not only is there another universe out there in a random direction, but if you travel far enough along that line, you will run into a duplicate of yourself doing exactly the same thing that you are doing at this very moment. This is all pretty wild, but difficult to test. The issue is that there is no way for any of the multiverse's bubbles to interact with one another. Although they are unrelated, they do exist. Therefore, we are unable to simply hop in a rocket and travel to our closest neighbor. However, there might have been a few cosmic mishaps in our ancient past. Our universe had recently separated from the greater inflation-driven flow when it was younger. A small possibility exists that our universes momentarily overlapped before being irreversibly forced apart if another bubble universe just happened to form close to ours. That offers a way of testing the multiverse because the likelihood of it occurring is extremely low, yet not zero. Sadly, there are yet no signs from observations of the wider universe suggesting that we have been involved in a collision of this kind. Those experiments don't exactly support the multiverse theory, but they also don't rule it out either. All we have left is our theoretical understanding of the early universe, which is based on theories rather than actual knowledge. Our understanding of inflation is quite limited. We do not know what caused it, why it had the energy it did, or why it ended in our universe. We're not even sure if inflation inevitably results in a multiverse or if our own calculations are incorrect. Another such enduring enigma is the concept of the eternal recurrence or the cosmic cycle. The idea that the universe has been and will continue to be reborn in a never-ending cycle. Although this idea has its origins in ancient religions and ideologies, it is also present in modern cosmology. It dates back thousands of years to the time of ancient Egyptian, Greek, and Indian civilizations. The cosmic cycle was a deeply religious and philosophical idea among many cultures, in addition to being a cosmological concept. The concept that the universe is cyclical was frequently used to explain how life and death, growth and decay, and other natural cycles affect life on Earth. For example, the universe was thought to go through recurring cycles of creation and destruction in ancient Egyptian mythology, each lasting a certain amount of time. Similar cycles of creation, preservation, and dissolution, known as the kalpa, are seen in Hindu cosmology. It is thought that this cycle never ends and that a kalpa lasts billions of years. Among the most interesting features of cosmic cycles is the possibility that a recurring pattern exists in universe itself. Over time, a number of cyclic models have been developed, including the oscillating universe theory. A cosmological concept known as the oscillating universe theory combines the Big Bang and the Big Crunch into a single cyclical event. That is, if this theory holds true, then the universe in which we live in exists between a Big Bang and a Big Crunch. According to the Big Crunch theory, the universe will eventually stop expanding. It will then start to shrink. The universe will get hotter as it gets smaller. This can be viewed as the opposite of the Big Bang. The universe will contract and get hotter rather than expanding and cooling. Everything in the universe will eventually collapse into a single, small spot where it all started. The idea was that each Big Crunch would be followed by a new Big Bang, tracing an endless accordion of expansions and contractions. This description would only mean one thing: all the laws of physics will be thrown out of the window. For physicists, this is simply unacceptable. To worsen the situation, some cosmologists even hold that the universe will eventually collapse in on itself after reaching its greatest peak of expansion. This will essentially lead to the same conditions as when we extrapolate back to the moment of the Big Bang. In order to solve this mystery, some scientists are suggesting that maybe the universe won't reach the singularity after all. The universe will instead return to an expanding state due to repulsive forces brought about by the quantum effects of gravity. An expansion, or Big Bang, following a collapse or Big Crunch, such as this, is aptly called a Big Bounce. The bounce signals the end of one universe and the start of another. The probability of a Big Bounce, or even a Big Crunch for that matter, is however becoming negligible. According to the most recent observations of the cosmic microwave background radiation, the universe will probably continue to expand until it comes to an end in a big freeze or heat death. Currently, CMBR measurements are collected using the highly precise Wilkinson microwave anisotropy probe. The age of our universe has been determined with extreme precision using the same equipment. Therefore, it is extremely unlikely that discoveries about the expansion of the universe in the future will significantly differ from current understanding. Nevertheless, a more thorough comprehension of one mysterious entity might change the odds, like the dark energy. We may have to put the oscillating universe theory on hold unless its true properties are drastically different from what it is now showing. In the conformal cyclic cosmology model, proposed by Sir Roger Penrose, each eon begins with a Big Bang event, followed by an expansion phase where matter and radiation dilute and cool. Eventually, the cosmic microwave background fades, and galaxies drift away as the universe enters a phase dominated by dark energy. Time becomes meaningless, and conformal rescaling takes place as the cosmos gets closer to its final state of cold, disordered nothingness. The result is a smooth, cold, empty universe that serves as the beginning of the next eon. A conformal rescaling is a stretching or shrinking that maintains all relative angles. Penrose uses that because you can use a conformal rescaling to make something that has infinite size into something that has finite size. The infinite thing that you rescale is not just space, but space-time. You rescale them both, and then you glue the end of our universe to a new beginning. Mathematically, you can totally do that. Most importantly, this cyclical process suggests that there is no beginning or end to the universe, and that the large-scale structure that has been observed is an ordinary consequence of this ongoing cosmic evolution. The possibility of observational evidence is one of the most interesting features of this model. Penrose has proposed that the cosmic microwave background radiation may have round patterns called Hawking points that represent remnants of earlier ages. These spots, which carry the name of the physicist Stephen Hawking, are locations where previously existing black holes have vanished and left behind traces in the cosmic microwave background radiation. There is still disagreement in the scientific community on the accuracy of certain studies that suggest they have found potential Hawking points in the CMB data. Others argue that more research is required to support or disprove the presence of Hawking points as proof for conformal cyclic cosmology, as the observed patterns may be the result of chance or instrumental effects. The conformal cyclic cosmology model would significantly change our knowledge of the universe if it turns out to be accurate. The model provides a fresh viewpoint on the nature of time, the development of cosmic structure, and the destiny of the universe by putting forth a cyclical structure rather than a single origin. It also raises interesting queries concerning the function of information, causation, and entropy over eons. Following research in this field are likely to focus on improving this model and looking for stronger observational support. The James Webb Space Telescope is also providing useful information for testing the predictions of the conformal cyclic cosmology model. Further developments in theoretical physics, including the creation of a quantum theory of gravity, could aid in the reconciliation of the model with alternative cosmological models. Penrose's conformal cyclic cosmology theory differs from the Big Bounce theory in that the expansion in conformal cyclic cosmology never reverses. In the Big Bounce theory, the universe slows down and eventually reverses into contraction, then reaches a high enough density to begin expanding again in a new Big Bang. Recent discoveries in various fields of physics and cosmology have provided potential evidence for cosmic cycles, like in the cosmic microwave background, which serves as a valuable tool in understanding the early universe. Researchers have found potential evidence for this model in the CMB's patterns, which may indicate the presence of events from previous eons. The other enigmatic elements of the universe, dark energy and dark matter, have baffled scientists for decades. But according to some theories, they might be quite important in cosmic cycles, with dark matter possibly triggering the universe's final contraction and dark energy causing its accelerated expansion. Also, the detection of gravitational waves from colliding black holes and neutron stars has opened up a new window into the universe. Some researchers believe that studying these waves may reveal clues about the universe's cyclic nature and help test various cyclic models. Whether it comes from modern cosmology or ancient philosophy, the concept of the cosmic cycle has a significant impact on how we see the nature of the universe and our place in it. If the universe truly follows an eternal cycle, it challenges our notions of linear time and the uniqueness of our own existence. It raises questions on the nature of time and life's greater purpose. Furthermore, research into the cosmic cycle and its potential implications to modern cosmology can shed light on the fundamental laws governing the universe. The ancient idea of the cosmic cycle may hold the key to solving some of the universe's greatest riddles as our understanding of the cosmos increases. Philosophers, theologians, and physicists have all been fascinated with the idea of the cosmic cycle. The concept of a constantly repeating universe may provide important new insights into the nature of existence as we continue to investigate the secrets of the universe. Higher dimensions of space are also a requirement for string theory, which postulates that what we see as elementary particles are actually strings of energy vibrating in several more dimensions than we can see. According to those theories, the other dimensions are compactified or curled up on themselves. So even if you were to find one of those new dimensions and embark on a voyage, you wouldn't be able to travel very far before returning to your starting point. But what if an extra dimension can hide an entire universe? A theory regarding the structure of the universe, formulated in the early 2000s, proposes that humans could reside in a three-dimensional brain surrounding a more larger space with 4 spatial dimensions, plus time. There may be another 3D brain holding another universe inside that higher dimensional bulk that occasionally might collide with our own. This theory's originators called it the ekpyrotic model of the cosmos, after a Greek term for conflagration, a nod to the fact that each cosmic collision would result in the fiery conditions of the Big Bang, and could explain the origin and eventual fate of our universe. In this model, the brains alternately move toward each other, collide, and then move apart again in an endless cycle, going from Big Bang to expansion to Big Crunch, and back to Big Bang. The patterns of structure we see in the cosmos today in distributions of galaxies and clusters are in this model, seeded by the interaction between the two brains in the slow collapse phase before the bang. Although the idea of proposing new universes and higher dimensions to explain the Big Bang may appear extravagant at first, there are good reasons why physicists take these ideas seriously. You've probably been misled into thinking that the standard view of the early cosmos is simpler than it actually is. When you think of the Big Bang, The first thing to come to mind is likely to be a singularity, an infinitesimal point of infinite density containing all of space and time that suddenly explodes out to create the entire cosmos. That idea became popular because Einstein's equations of gravity can describe a cosmos that begins that way and perhaps wraps itself up with a big crunch singularity at the end. But it doesn't work with what we see in our observations. We can see the afterglow of the Big Bang and background light just at the cosmic horizon, which indicates that a simple evolution from a singularity to the big, amazing universe we live in today now just doesn't make sense. The problem is that the cosmic microwave background, the remnants of the Big Bang, is too perfect. It is identical to an incredible degree of precision, 1 part in 100,000 in all directions. Same spectrum, same intensity, same color, or given its microwave light frequency. That's troublesome, since there is no justification for 2 locations on different sides of the sky to match up that way. Even if everything started together, wrapped up in a singularity, the way it expanded outward should have introduced extreme differences in different parts of the early cosmos. In the expanding stage of cosmic evolution, regions that are currently separated from one another never had a chance to get on a common temperature. On one side of the sky, the cosmic microwave background should differ significantly from the other. From what we've seen so far, inflation seems to work well with our current paradigm and even nicely explains the little 1 part in 100,000 fluctuations observed in the cosmic microwave background light. But we don't have what anyone would call solid proof that it happened, nor can we say how or why it started, or what drove it. And likewise, it's not entirely possible to get hit by another universe even in the inflationary scenario. 2 bubble universes might at some point collide, leaving imprints like bruises on each other's background light. If inflation did happen, the sequence of events that created our observable universe could have occurred time and time again in different parts of a much larger space in a process called eternal inflation. The theory states that while the larger background space is always expanding, inflation sometimes stops in a small portion of it, which causes that region of the universe to heat up and give way to normal cosmic expansion. As a result, little bubble universes, identified by their distinct post-inflation zones, would continuously emerge from the expanding background, giving rise to a kind of multiverse. Astronomers have searched for such bruises. Though none have shown up yet, they'll keep searching. The ekpyrotic model has been revised several times over the years, and the most recent iteration does not suggest cosmic collisions or higher dimensions. It looks similar to inflation in certain aspects. Instead of being pushed by brain motion, it is driven by the evolution of a scalar field, a type of space-filling energy field like to the one that most physicists believe drove cosmic inflation. Despite no longer requiring grand cosmic collisions, the ekpyrotic model still includes a transition between a collapsing universe and a Big Bang. The cosmic horizon, defining our observable universe, is a hard limit. We can't see beyond it. And unless our understanding of the structure of reality changes drastically, we can be confident we never will. The expansion of the cosmos is speeding up. Anything beyond our horizon now will be carried away from us faster and faster, and its light will never be able to catch up. While we might never be able to say with certainty what lies beyond that border, what all the theories have in common is that our observable universe is part of a much, much larger space. Whether that space contains a multiverse of bubbles, each with different physical laws, whether it's part of an ever-growing cosmos of which we are only one part in one cycle, or whether space extends outward in directions we can't conceive, we currently just don't know. But we're seeking clues, the patterns in the cosmic microwave background light, the distribution of galaxies, and even experiments testing gravity and the behavior of particle physics are giving us insight into the fundamental structure of the universe and into its evolution in its earliest moments. We are getting closer and closer to being able to tell our whole cosmic story. We can already see directly the fire in which our universe was forged, the moments just after its beginning. With the clues we are gathering now, we might someday follow the story all the way to its end. Our understanding of the universe has massively evolved over the course of our own evolution. Actually, the beauty of science lies in how little we yet know. Currently, some of the world's best minds are delving into the questions of what the universe really is, and what, if anything, is beyond. Like many mysteries, like Pluto, the truth is that it all depends on how we define it. Is the universe everything that exists, or is it something more limited? Just another aspect of all that exists? And is there another one like it out there? There are an infinite number of possibilities, ranging from worlds inside black holes to universes other than our own. One of the most intrinsic human parts about us is our ability to wonder, to dream, and to imagine. Thanks to this, we have several theories about what lies beyond, or is bigger than our universe, that line up with at least certain current observations, physics, and math. The possibilities are endless. As we gaze at the stars, let's remember that our curiosity transcends boundaries. The universe, whether finite or infinite, beckons us to explore, to seek answers, to dream, and to wonder. Perhaps the greatest discoveries await us beyond the cosmic veil.